Hello, my name is Austin. I'm going to be showing you guys how to do part two of Dr. Osbay's ANSYS Fluent project. So to start, I'm going to be selecting Fluid Flow Fluent and drag it over. I'm going to create a standalone system. Right click on Geometry and click New Design Model or Geometry. Double click that, let it open. Once that is open, wait till it fully opens. And then I'm going to go to Sketching. I'm going to go to Rectangle after I select the Z-axis. Go to Rectangle. I'm going to select this central piece here. You can zoom in to get a little closer. And I'm going to pull out, it doesn't really matter the size because I'm going to be dimensioning it. So I'm then going to go to Dimensions. This project requires that you have a horizontal distance of 100 centimeters. So I'm going to select Horizontal. I'm going to select these two lines to dimension it. Put up right here. And then down here, it's going to populate, and I'm going to put in 1 meter. Then we have to do the vertical because we don't want this thing to be non-dimensioned. And I'm going to do 0.5 meters, so 50 centimeters. So now we have our block. We're then going to go back to modeling. We're going to go to Concept, Surface from Sketches, and then it's going to ask you for a base object. You're going to go to the XY plane sketch, click on that, click Apply, then you're going to click Generate. So we now have our 100 centimeter thin horizontal flat plate, and that is ready to go. So I'm now going to save this part. I'm going to save this as just sample. That is saved. We'll let it start saving. Now we're going to open the mesh. So you can either double click mesh or click edit. Either one works. Let that open up. Takes a second to open this up. So this is where the meshing is done. You're going to click Z-axis again. Let's get it on the XY plane. Now it's time to start meshing. So we're going to right click. We're going to click face meshing because we want to do face meshing. You click the geometry. We're going to click apply here. Now we have face meshing. And then we're going to actually do some sizing, which should help us get a more uniform mesh. So I'm going to actually control click the top. Oh, forgot that. Edge select first. Control click the top and the bottom. And then we're going to click apply. But we don't want to do it by element size. We want to do it by number of divisions. We also don't want capture curvature, and we also want it to be hard. So for the top and bottom, since it's longer, we're going to want to do, from what I've done, 450 divisions. That should give us, pretty good mesh. So this is looking good. I can mesh it right now to show you guys what it would look like. So this is good and all, but we really care about the section down here. So we're going to do a little bit more mesh refinement. We're going to now select only the front side, click apply. And then again, we want number of divisions. However, this is half the size of the first one, so I'm going to do half the size of this. We're going to do 225 divisions. Again, we don't want that capture curvature. We want it to be hard. And then this is where you can really make the mesh a lot better with bias. So these dots are just where it's biased. So obviously you can see this one's more biased here, this one's more biased here. So we're going to click the top one. And then this bias factor determines how biased it is. I'm going to do 95% because we really care about that boundary layer. And once that goes into effect, you can see it's much more dense down here. We're going to update that mesh. And as you can see, it gets more refined to this corner. But we care about the whole boundary layer, not just the front. So we're going to insert another sizing, this time selecting the backside, doing the exact same thing, the same number of divisions, 225, the same capture curvature is no, the same hard, and then this time, same bias factor, but we're going to reverse it. Because as you can see, it's trying to do it up here. We don't want that. So So we're going to select this, we're going to click apply, and it's now doing it down here. So now when I update this mesh, I should get yep, exactly what I wanted. So we have a coarser mesh up at the top, which we don't really care about the top. We care about the bottom. As you can see, it gets significantly finer as we go in, which is good. It's perfect. That's what we want. And then just so you guys know, if you click statistics here, it'll tell you your nodes and elements. Nodes are the actual points. Elements are the space in between the points. And in this one, let's see, these would be the nodes. This would be the element, but that's too much. So we have it all meshed, but now we have to do some name selection to make it easier for later. We're going to select the top surface, create name section. This is going to be the this is just what I call it, the far field pressure. That's good. Then this one we're going to call the plate, as this is the thin plate we're going over. We're going to call this one the inlet. And then we're going to call this one the outlet. Pretty simple naming, nothing crazy. Let's double check everything. Oh, and then to make our lives easier, I'm going to name this the airflow. Okay, cool. So we have airflow here, we have the airflow selection, we have the outlet back here, we have the inlet in the front, we have the plate, and we have the far field pressure. Perfect. We have our face meshing, we have our edge sizing, 450 on top and bottom. We have our 225 divisions on the front with a bias towards the bottom, 225 same with a bias towards the bottom, and our mesh looks very good. So I'm going to save this as we now have a good amount of mesh. And on to the next step. So we're going to have to update this mesh on here so it recognizes it for the next step. Then we're going to go to setup. So this is where we really set up the sim. We're going to want double precision. And then this is really important in the solver processes. One will only use one core on your computer. So you want to, if you want it to run as fast as possible, you want to maximize this. So I have 6 cores on my computer, so I'm running 6 cores. We're going to start that. This one takes a second to load. It also puts your CPU usage to 100. But let's let this load. Take a second. Almost there, almost there. Okay, cool. So we're in. First thing we want to do is go to models. So this project says it's viscous laminar. So we're going to click on viscous and we're going to click on laminar. Boom. We got viscous laminar down. Now we need to set our air. So we're going to go to materials, we're going to go to fluids, and we're going to double click on air. It gives us, by Dr. Osbe, 1.2 kilograms per meter cubed. Perfect. And then for viscosity, 1.8 times 10 to the negative 5. So we're just going to change that real fast. Make sure you don't click close. Make sure you click change create or make save. Click it a couple times just for security, and I checked it. It's good. So now we have that set. So now we got to set our velocity, which Dr. Osbe says 2 meters per second. We're going to put 2 meters per second. Another thing to do, we want to select our symmetry. So I'm going to right click this far field pressure. I'm going to go to type and I'm going to put symmetry. So make our lives a lot easier down the road. And I'm going to double click on inlet and we're going to set our velocity magnitude to 2 meters per second, which is exactly what we want. Apply that. I'm going to double check it just because I'm paranoid that it didn't save. So we have our viscous laminar, we have our air statistics here, 1.2, 1.8. We have our inlet velocity at 2. We have our symmetry. We're getting there. Now we have to set our residual. So we're going to go to monitors here. We're going to double click on residual. We want, when we do this calculation, we want the criteria to be 10 to the negative 6. We're going to add 3 zeros to what it automatically gives you. We want our solution to be accurate. So you're going to click OK. And then I'm going to double check, make sure, yep, 10. 10 to the negative 6, looking good. And then now we're ready to run the calculation. We're double click on run calculation. This number right here, the number of iterations, it's only really like a limit. So I just put it 10,000 because I know we're never going to get there. And then you click calculate. Yes. So it's going to start running through these, and then it'll give you a nice graph here where it's going to show you the iterations. And these two are going to get to 10 to the negative 6. They're already at 10 to the negative 6. We're good there. It's this top one here, the continuity, that we're going to have to wait. Shouldn't take too long. If you're getting hundreds of iterations, you probably did something wrong, because it really should not take that long, or maybe your mesh is too refined for your computer. Okay, calculation complete. This step is done. Again, as always, I would suggest you save your project. I've lost my project before because ANSYS gave me a licensing error. Okay, so we're saved here. Writing results done. We're gonna go back to here. Then we're gonna go to CFD post, which is in the results section. So this is where we're gonna do all of our stuff to get our values. So the first thing Osbey asked for is to get the velocity with vectors and pressure contours around the flat plate. So we're going to do the velocity with vectors first. As always, click the z-axis. So we want it with vectors. This is a contour. This is with vectors. So let's click this. We're going to name it velocity. Velocity profile vectors. Cool. We got our vectors. All right, so we want our location to be symmetry 1. This is where the symmetry goes in. You guys can mess around based on your mesh. This reduction factor is going to change. It's essentially reducing the amount of curves that you get. I found 12 works for me to make my graph look good. It's going to be different for everyone. I've also found that arrowhead works really well, and I'm reducing the size by half. So now I click apply. Boom. We have our nice velocity profile graph. And then if I zoom in, which you zoom in with your scroll wheel, and then if you control and then click with your scroll wheel, you can screw it over. You can see that boundary layer is essentially not there. And it starts forming. And as you go along, the boundary layer just gets bigger and bigger, which is what it should do. If you're not seeing this, then you did something wrong on your simulation. Go back and check all your stuff. So with this there, we have that. Perfect. Next step, let's get our pressure contour. So we're going to go back up here. We're going to click contour. I'm going to call this our pressure contour so there's no confusion. Okay. So we want pressure selected. We don't want our location to be far field pressure. We want it to be symmetry 1 because we want this whole thing. And then this number of contours, if you do 11, which I'll show you guys actually just so you can see what that does for you, it's going to look like not great. As you can see, yeah, it's only got 11 colors. So we're going to do 1,000 because I like good looking graphs. So this looks very good. You can see the pressure is peaking here right at the start before the boundary layer forms. And this is a good telltale if your mesh is good, because if your mesh is very coarse, you're going to get a larger region of red because you don't have a fine enough mesh. So this being really small is a good thing. And also you can see that red in the background. That's just the velocity profile. We can just hide that, get that gone. So yeah, this is looking good at the boundary layer. As you can see the pressure decreasing as you go along. Looks very good. Okay, also yeah, it does that sometimes. So let's scroll way back out, get this centered. All right, so we got those. Now we have to plot our velocity profile at 35 centimeters and at 75 centimeters. So to do that, we're going to have to create some lines. So I'm going to hide our pressure contour real fast, and then we're going to start making some lines. So first thing I'm going to do is actually make the plate line, just because we're going to need that for skin friction and stuff like that. So you have your X and Y coordinates here. So for the plate, I want it to be this exactly. We're going to click apply, and as you can see, it's creating that line there. We're going to do it again, but this time, for some reason, it won't let you put numbers first, so centimeter 35. It's going to be our 35. So we're going to do, this is in meters, so 0.35. And then we're going to put 0.35. I'm going to put 0.35 as well. And then for this one, our height is 0.5. So that should be good. And then again, I want 1,000 samples. I want it to look good. Perfect. It matches our points. Now let's add the 75 centimeter one. Looking good, looking good. 75 centimeter, where'd you go? Here, 0.75. For some reason, it doesn't show up in the tree until you click apply for the first time, which I find pretty interesting. Let's make sure these values are correct. Let's do 1,000 samples, and bang, we got all of our lines that we need. So now we can create our velocity profile chart, which is going to be here. So we're going to click that chart. I'm going to call this the velocity profile. That's not spelled profile. Velocity profile. Okay. So again, velocity profile. Okay, cool. So for our data series, I like labeling it. It makes it a lot easier when you go back or staying organized. So we're going to say x equals 35 centimeters, and we're going to click that line. So this is now putting that line as the location where it's pulling the data. And then we're going to add a second series because we want to, put them both on the same graph. X equals 75 centimeters. And then again, we're going to select that centimeter 75, and you can see it shows it here. Looks good. For the x-axis, we want the velocity in the x, so velocity u. For the y-axis, we want the y-axis. So that should be good. Let me make sure there's nothing I'm missing here. I think we're good. Let's apply it. Perfect. This looks great. So you can see that the boundary layer is taller at the 75 centimeter than at the 35 centimeter. And you can see I set my velocity as 2, and it's coming right back to that 2, or as close as it can be since it's solving for it versus the perfect solution. So now that we have that, we can move on to wall shear stress. That's another one we can do in CFD post. So I'm going to create another chart. We're going to call this wall shear stress. Click OK. I'm going to type again. Axis. Stress. Perfect. Now we're going to go to our data series. Series 1 doesn't really matter since we're only going to have one data set. And this time, this is where having that plate line is important. We're going to click plate. For our x-axis, we're going to do x. For our y-axis, that's where it gets fun, we're going to do wall shear. So now, when I click apply, and you can see this is the effect of not having a lot of samples. Let's go back to our, that's not what I meant to do. Plate. That is because when I made these, didn't make the sample 1,000. The rest were 1,000, so wasn't. So you can see the line, fix itself. And this makes sense. The wall shear is the highest when your boundary layer is not formed yet. And then as that boundary layer forms, it quickly decreases the wall shear. So this is everything that you can do in CFD post. But we still have a couple things we need to do: the skin friction coefficient and the drag coefficient. So those are going to be best done back in the previous step where we were. So let me save this real fast. Saved. Perfect. We're going to go back into solution right in here. And this is pretty easy. So we're going to go to plots because we want to do the skin friction coefficient first. So we're going to click XY plot. Well, we're going to right click XY plot. We're going to click new. I guess you could double click it as well. I don't really care about naming it. We're going to do wall fluxes. And then we're going to click. You can do wall shear stress in this one, but I'm going to click skin friction coefficient. And then we're going to do it on the plate. And then we're going to plot that. And would you know, it's very similar to the wall shear stress, which makes sense. Like I said, as your boundary layer is forming, your skin friction coefficient is going to go down. So that is good. Now to the last thing is drag coefficient. And for some reason, they put it in an interesting spot. It's in report definitions. You're going to right click that. You're going to go to new. You're going to go to force report, and you're going to click drag. It's automatically going to select drag coefficient. And then this is where, again, that plate zone is important. We're going to click plate, and it's actually going to print it out down here. Don't click OK, just click compute. Bang. There's your CFD, your CD. 0.016 is for my run. And then just making sure we got our velocity with our vectors, we got our pressure contour, we plotted our velocity profile, we plotted the wall shear stress and the skin friction coefficient, and we got our drag coefficient using Fluent. Now, obviously, the boundary layer thickness, you can solve that in your Excel. And then with the velocity profile, you can compare it with the Blasius velocity profile, which that can be done also in Excel. Pretty much all of these you can export. Like if I go back to this, you can export to a CSV and put it into Excel, which is what I would do. So you can compare these two to the Blasius. But that's it. I hope this was helpful in showing you how to do this simulation. Thank you.